Hello everyone, welcome to our channel Code with Sunny, and in this video we will be talking about the problem count binary strings of educational code forces round 140 rated for division 2. Okay, so this problem is quite tricky one where we are going to discuss the dynamic programming solution for this problem, and also we are going to discuss the DP states, how we are going to transform from one DP state to the other DP state and adding all the valid answers. Okay, so make sure that you watch through the entire video where we are going to discuss all the concepts related to this problem for the dynamic programming. Okay, so yeah, so let's begin. So you are given an integer n, and you have to calculate the number of binary strings meeting the following constraints. So these are the constraints. Okay, so yeah, I will discuss all these constraints in short. Also, if you haven't read this problem, I would suggest you to read this problem at least once, so that you would be aware about what the problem is going to ask. Okay, so we need to count the number of binary string s of length n meeting the aforementioned constraints. It means that these three constraints should be satisfied. If we have been given aij equal to 1, it should be satisfied for the subarray I from I to j. Okay, and we need to find out the number of binary strings s that satisfy the above constraints. Okay, and finally we need to output the number of binary strings modulo this prime number. Okay, so let's start to understand this problem in detail. Okay, so we are given the conditions. Okay, and the conditions is something like this: if aij is equal to 1, if aij is equal to 2, and if aij is equal to 0. Okay, these are the three conditions. Okay, so let's discuss these conditions one by one. If aij is equal to 1 means the subarray from I to j inclusive has all the elements equal, Okay, so if aij is equal to 2, then the subarray I to j has at least two different elements. So you need to think about that is like this is a binary string, so at least two different characters means 0 and 1. 0 and 1 must be present. So if aij is 0, then no additional constraints. Okay, so how we are going to use these conditions to find out the number of binary strings that satisfy this one. Okay, and remember we have been given the I to j. Let me write down. We have been given the rules of ij. We have been given for each valid I comma j. Okay, let me write down for each valid I comma j, where I is going to be less than or equal to j. Okay, so we have been given the rules. Okay, for each subarray, suppose we have this array, we have this string s0, s1, s2, s3. Okay, so we have been given the data of s0 to like it would be something like this: s0, s0, s1, s0, s2, s0, s3. It means that aij can be either among these three values: 1, 2, 0. Okay, so the data given are for s0, s0, s1, s0, s2, s0, s3. Similarly s1, s1, s2, s1, s3. Similarly s2, s2, s3, and finally s3. We have all these data, and how we are going to use these data to find out the number of binary strings, number of valid binary strings. We need to find out that satisfy the above conditions. We have been given the data, whether let's say the data for s0 to s2 says that a of 0 to is going to be equal to, let's say, 2. It means that the subarray from s0 to s2 must contain at least two different characters. It means that s0 to s2 must contain 0 as well as 1. So the string can be 0, 0, 1, or it can be like 0, 1, 0 also. It can be 1, 1, 0 also. Okay, like this is for s0 to s2, s0, s1, and s2. So we have been given all these data. We need to find number of valid binary strings of length and that satisfy the given constraints. Okay, so let's take an example and let's understand how the things will work. Suppose we have this 102, 10 and 1. So we have the n as 3 and we have the data as 102, 10 and 1. Okay, now again the strings are something like this: s1, s2 and s3. Okay, so we have been said that substring from s1 to s1, it means this part, is equal to the condition for this is given as 1. It means that the single character must, like the substring must have all the same characters. Since the substring size is 1, it is always satisfying this condition. Okay, and again let's move out to the next part, s1 to s2. It says that the condition is 0. It means that there is no condition over there. You can put any character in this s1 to s2 part. And now we have s1 to s3. You can see it says that it must have at least two different characters. It means that 0 and 1 must be present in this substring. Okay, now you can see there are 3 positions, so there are 2 power 3. It means 8 possible different combinations we can get. So it would be something like this: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now you can see there are 8 possible different strings you can get of length 3. Okay, now which are valid strings and which are invalid strings. Okay, now a string is said to be valid if it satisfies this condition. Okay, now you can see let's focus upon let's try to eliminate those invalid strings. Okay, now you can see this is invalid and the last one is invalid. It means that 111 and 000 are invalid because if you look out for this condition, it says that substring from s1 to s3 must contain at least 2 different characters. Now you can see if you pick up this one, all the characters are same, like it doesn't have 2 different characters. Similarly this one, it means that these 2 are invalid and rest are all valid. Okay, hence the answer for this is 6. You can see we are getting the 6 as answer. Okay, now this is for the explanation part. So how will we frame our dynamic programming solution? Okay, so we'll start with the dynamic programming. Okay, now before we move on, let's consider the simple fact, like what if aij equal to 1 is not given. Suppose, let me write down suppose aij equal to 1 is not given to us. So you can see we have only these 2 conditions. Now you can see we can easily answer what is the number of valid strings of length and that we can have. Now aij equal to 1 condition is being added over here, so we will use this condition to frame our dynamic programming solution. So how we will try to use this one, let's try to understand that. Okay, so let me erase this one. Where is the page? Okay, so we will try to answer dp of I. Let's define dp of I state as number of valid binary strings of length I that satisfy the conditions that can be given to you. We are calling it as valid because it is already satisfying the set of conditions so far up to the length I. Okay, so how will you use the condition for aij equal to 1? Okay, so let me change the color first. So we have this one as aij equal to 1. It means that the subarray from I to j will have equal elements. Okay, so what we will do is we will try to frame our dynamic programming solution in such a way. So let me write down the approach. Okay, so it would be something like this: for each I in range from let me write down, for each I that belong to 1 to n, we will iterate our g for each j that belongs to 1 to I. Okay, now we are just trying to make sure that the subarray from j to I. Okay, now it would be something like this: we are at I, we are over this position I, and we have this position as j, and this is the subarray from j to I, and we are talking about this subarray. Note that this subarray includes j as well as I. Okay, now we are just iterating for for each I that belongs to 1 to n, and for each I we are just having j. For each j that belongs to 1 to I, we have the subarray as j to I, and we will claim that the subarray, let me write down, sub of j to I has all equal elements. If we claim that this subarray has all equal elements, then we can easily say that our answer for the ith state will be dp of I plus equal to, all the subarray from j to I will have equal elements. Then number of ways to form the binary strings of length I that ends at position I as well will be equal to dp of I plus equal to dp of j minus 1. Means the strings that ends at j minus 1th position will be just added to the ith positions, right? Because all the elements are equal, we have subarray from j to I being all the elements have equal, so we will just add up the number of ways to reach the position I, okay, with the value that we get from j minus 1. So dp of I plus equal to dp of j minus 1. Okay, now the very important condition is how you are going to check that this is going to be valid. So we have just claimed that subarray of j to I has all equal elements, so we have to check the subarray from j to I has all equal elements. So we have to check if subarray has from j to I has all equal elements. So how we are going to check? So it must be satisfying, means the subarray from j to I must satisfy the conditions that is being given into the problem statement. Okay, so let me write down in the next page. So we have from I belong to 1 to n, okay, and we have this j belong to 1 to I. Then we have this subarray from j to I must have all elements equal. Also it satisfy the rules. It must also satisfy the rules. The rules means this is the matrix, like let me zoom in. So this would be with a matrix format. It would be something called right triangle. Okay, this will be given for each index. It means that for each subarray we have the data, and we have to check if subarray from j to I is satisfying the above rules or not. Okay, so we have to check if that satisfies. It means that our number of ways to reach to the ith position will be equal to dp of, will be added with dp of I plus equal to dp of j minus 1. Okay, if the subarray j to I has equal elements. Okay, so this is like for aij equal to 1, we are using this condition aij equal to 1. This is the main condition that we are going to use to find out the required strings of length n. Okay, so how we are going to check that part? Okay, so it is going to be very much simple. Suppose we have we are at position j, and the positions are j plus 1 and the positions are j plus 2, and it goes on up to the positions I, and we have this position 1 and we have this position 2, and it goes on up to the position j. Okay, now we have to check if all the elements including this j and including this I are equal. And how we are going to check that? So must satisfy rules. Okay, now we have this rules. We have the subarray, we have the data for each subarray, for each subarray in the range from, if you can pick this subarray, you can pick the subarray up to this part, you can pick the subarray up to this part, like any subarray in range from j to I. Okay, now we have the following data. If aij is equal to 1, it means that the subarray from I to j are equal. If aij is equal to 2, it means that distinct, it must have at least 2 distinct elements. If aij is equal to 0, it means that no condition, right? And we are just trying to find out if the subarray from j to I has all elements equal or not. Okay, So what we will do is, for this to check, we'll just check if there is a subarray in the range from j to I that may also cover the indexes j and I. Okay, so we will just check if there is a subarray from j to I such that a of x, it would be something like this, a of xy is equal to 2, then this condition will become false. Okay, so what we are just trying to say that for j to I to have all the elements to equal, there must not be a subarray that satisfy this condition a of xy will be equal to 2, such that x must be greater than or equal to j and y must be less than or equal to I, and x should be less than or equal to y. Okay, so if there is an element a of xy equal to 2, it means that there is at least two distinct elements in the subarray like this one. If that is present, it means that subarray from j to I will not have all the elements equal. Okay, so we will try to check it. If a of xy is equal to 2 such that x is less than or equal to y and x is greater than or equal to j and y is less than or equal to I, if this condition is found for the subarray j to I, then we can say that all the elements are not equal. So we will not add this condition. So we are just trying to add this one, right? So we are just trying to add dp of I plus equal to dp of j minus 1. So if this condition is present, then we will not add this one. Okay, so this is the one of the thing you have to check. And the other thing you have to check is something like this. Okay, so what I've said is these j and I must have all those elements equal. So one of the condition is a of xy equal to 2. You have to check in this part subarray. And the other condition is you have to check whether like we are just claiming that from j to I all the elements are equal, and from j minus 1 and from j minus 1 position this is going to be such that a of s of j minus 1 will not be equal to s of j, right? So this partition will be in such a way that s of j minus 1 will not be equal to s of j. So we are just trying to say from j to I all the elements are equal, and from j minus 1, like at the position j minus 1, s of j minus 1 will not be equal to s of j. Okay, so we are trying to check if the subarray from j to I have all the elements equal or not. Okay, so there is one more condition you need to check. So for each subarray whose left index will be less than or equal to g, sorry, whose left index will be strictly less than g, and whose right index will be greater than or equal to j, if there is a subarray something like this. Okay, so suppose there is a subarray something like this, and the value is a of xy is exactly equal to 1. It means that all the elements are equal from here to here. It means that this condition subarray from j to I will become false. So we are claiming that from j to I all the elements are equal, and s of j minus 1 will not be equal to s of j. And if you are able to find a valid xy such that x is going to be strictly less than j and greater than or equal to 1, and y is going to be something like this, y less than equal to n and greater than or equal to j, and a of xy is exactly equal to 1, it means that all the elements up from here to here are equal. Okay, so it means that you are not going to find this j that you have chosen such that j to I must have all the elements equal is not a valid j. Okay, so in that case you must not also add this condition dp of I plus equal to dp of j minus 1. So you are not going to add this condition. So this index j that you have chosen becomes an invalid index. Okay, so overall you have to check two conditions. Okay, so let me write down these two conditions that would make you more clear. So suppose you are at index j and you are trying to check if this is a valid index or not. Okay, so you check two conditions. If a of xy is equal to 2 and x is going to be greater than or equal to j, and y is going to be less than or equal to I, and x is going to be less than or equal to y. So if a of xy is 2 and x is greater than or equal to j, y is less than or equal to y, and x is less than equal to y. Okay, so it means that there is a subarray in the which is actually a subarray of the actual, let me write down, if there is a subarray such that a of xy is 2, which is a subarray of this j to I array. Okay, so if that we are able to find, it means that there are at least two distinct elements and the index j is not a valid index. Similarly, if I will say a of xy is equal to 1 and x is going to be less than j and greater than or equal to 1, and y is going to be greater than or equal to, it should be something like this, and I, so it means that there is a subarray something like this, uh, and all the elements are equal. It a of xy equal to 1 means all the elements are equal. It means that j is again not a valid index. If any of these two conditions becomes true, you are not going to add the number of ways dp of j minus 1 to your answer. Otherwise, if both the conditions becomes false, you are going to just add dp of I plus equal to dp of j minus 1. You have to do this thing, and you have to do this for each index I. Okay, so let's try to look out the code how everything will be implemented easily. Okay, so this is the code that I would love to share with you. Okay, I hope the screen is visible. So okay, so we have this dp of n plus 1, dp of I is number of valid strings of length I, and we have this rules. Okay, so rule of ij is 0 means no condition, rule of ij is 1 means all the elements are same from I to j subarray, and rule of ij is 2 means at least two different, means 0 and 1 must be present. Okay, so we are just taking the input for each subarray. We have the data as rule of ij. Okay, and also if rule of ij is 2, it means that, sorry, rule of ii is 2, it means that there is a, there's a subarray containing a single element and it is 2, and for rule of ij is equal to 2, it means at least two different. It means that we are just making ok as 0, and if ok becomes 0 finally, it means that total number of valid strings would be obviously 0 because of this condition. Okay, so otherwise let's try to generalize our answer. Okay, so we are trying to use this base case dp of 0 as 2 because there would be two possible characters, 0 and 1. So we will write down dp of 0 as 2. So and we will try to fill up for each I. So we will try to iterate for each j, and we will check if the j to I subarray has all elements equal or not. If it is equal, so ok will remain as 1, and we will just add dp of I plus equal to dp of j minus 1. Okay, so we need to check if the conditions are true or not. Means ok will remain 1 as not, it means subarray j to I has all the elements equal or not. So first of all, we will check this condition. E of xy is, if there is an subarray which satisfy a of xy equal to 2, x greater than or equal to j, y less than or equal to I, and x is going to be less than or equal to y, then this j to I subarray will not have all the elements equal. It means that it is just violating the criteria of conditions. It is violating the criteria of rules that we have taken the input. So we are just going to check. We'll just iterate xg, and it will be we'll be starting with x equal to j and x less than equal to y, and also we will be checking if ok remains as 1. Okay, also y less than I, and ok remains as 1, and y plus plus. If there is a rule of xy as 2, it means that the subarray from x to y must contain two distinct elements, at least two different elements, but we are claiming that j to I has all elements equal. It means that this j index is not a valid index, so we will make ok as 0. Similarly, we are going to try to check this condition. Okay, this condition will be checked. So we will start x from 1 and it will go less than j, and if ok remains as 1, and we will start y with j and y less than I. If there is a subarray xy which says that this entire subarray will have all the elements equal, but we have said that only subarray from j to I has all the elements equal, so this index j is not a valid index, so ok will become 0. Okay, and finally if we will check if ok remains as 1, we will just add dp of I plus equal to dp of j minus 1, and finally what will be our answer? Dp of n. So this is the entire code which will give you the accepted verdict. Okay, so also we can optimize this code by, there's no need to check these two conditions. Okay, so we can still optimize this one, and I have tried to use this optimization. We need to use some extra space to store all these things. Okay, so we have this we'll have this hash1 and we'll have this hash2. Okay, so in the previous part we have just checked if rule of xy is equal to 2. Okay, so it means that what actually we are trying to check is okay, so let me just erase all these things. Okay, so we are just trying to check if there is a subarray which has a of xy as 2. Okay, so we have just made another 2D vector that will help us to grab this condition efficiently. Okay, so we'll have this hash2. Okay, so we'll just populate the entries. If rule of ij is equal to 2, we'll just make hash2 of ij equal to 1. Okay, and we will just make for every subarray which contain this subarray as the inner part of this subarray. Okay, so it will be something like this. Suppose we have this subarray that says that a of xy equal to 2. Okay, so for each subarray where this let's say this subarray, let's say we are calling this subarray as p. Okay, so for each subarray which is actually containing this subarray p, like something like this one, we'll try to make all these subarrays has 2 of ij equal to 1. Okay, so when we are at this index j, we'll just check it out if hash2 of j to I equal to 1. If it is 1, it means that there is an index, there is a subarray that is contained in the subarray j to I and has a of xy equal to 2. Okay, so this matrix will help us to check that, and we'll just populate this one something like this. We'll start with the smaller subarray and we'll try to move to a bigger subarray length. Okay, and okay, so you can see we have just checked it out. If hash2 of gi is not equal to 1, okay, it means that there is not a subarray which is contained in the subarray from j to I and has the value as a of xy equal to 2. Okay, and there is one more condition, has 1 of j not equal to 1. Now this is going to be a little bit tricky. We have this has 1 a linear array that is going to store the elements. Okay, now what we have just trying to check is like let me just clear this one, wait a minute. Okay, so let me change the color also. Okay, so we are just trying to check whether j is a valid index or not. We have already checked this part, a of xy equal to 2. Okay, now we need to check subarray of something like this. Okay, so if there is a xy which is equal to 1 and all the elements from like the left end of the subarray must be less than j and right end of the subarray must be greater than or equal to j. If there is some valid xy that is equal to 1 and satisfying this condition, it means that j is not a valid index. Okay, so how we are just trying to store this information. So suppose we have this subarray, suppose from the rules we have the subarray something like this. Let's say a of m plus 1, not calling it as a, let's say s of m plus 1, s of m plus 2, and it goes on something like s of, let's say q. Okay, there is a subarray, there is a string of length q minus m plus 1. Okay, so let's say we have this data called as let's say we have the subarray sm something like this. Okay, and it sees that all the elements of this array are equal. Okay, and we have at a particular index, let's try to use some values. I think that would be better. S0, S0, S1, S2, S3, S4, S5. Okay, now we have this one S1 to S4 and it says that all the elements are equal. Now we are at a valid index. Let's say we are at this index j, which is called as S2. Okay, so we need to check whether there is a subarray which is of type this one, a of x equal to 1, whose left end is less than j and right end is greater than or equal to j. Okay, so if you are able to find this one, it means that j is not a valid index. Okay, so how we are going to use this information? So suppose we have got this position, let's say p up to q. Okay, so we will mark all the elements from p plus 1 to q, something like this. P plus 1 will be included in the interval, q will also be included in the interval. So we'll mark has 1 of let's say the index as I will be equal to true, which will be marked as 1. If you are able to mark that and if you are at index j, we will just only check if has one of I is equal to 1, if has one of j. Okay, so if you are at index j, if has one of j equal to 1, it means that there must exist a left bound, there must exist a left end which is strictly less than j, and other right end must be strictly greater than or equal to j. We are able to find that. So this condition, this linear array will help us to store that information. Okay, so yeah, we are almost done. So what in the finally we have to check if has one of j is not equal to 1 and has 2 of gi is not equal to 1, then we will just add up this condition and rest we are done. So this helps us in optimizing the code to O of n square. Okay, and yes, the time complexity is, in worst case we have this one also, so which will be O of n cube, and but the space complexity will remain as O of n square. So if you have any doubts in any of these solutions, you can just tell me in the comment section of the video. I would love to help you guys, and thank you for watching this video, and please do not forget to subscribe.